Unfortunately, we had a technical malfunction, so the last part of that, well, let's not talk about it, let's just do it right. Okay, we have y double prime minus y is t squared, and we were talking about why y can't contain a t cubed. Now, I proceeded to write some stuff in here as well as down here, but I'm going to rewrite this. I'm just going to point to this. If yp was t cubed, then the second derivative of yp would just be 6t, and our left-hand side would be yp double prime minus yp is 6t minus t cubed. You see that we have a t cubed here. We also have a t term, but the real difficulty is this t cubed term that we can't get rid of. Okay, we have a t cubed here, and nothing in a higher derivative can get rid of that t cubed term, so that our particular solution can't contain any kind of a multiple of t cubed. We could contain multiples of t that might take care of this 6t when we take all the derivatives. We might be able to eliminate the 6t in the process. Now, that probably doesn't make a lot of sense to you when you're seeing it right now, but you'll see a little more in a minute. Now, if yp was some quadratic polynomial, then its second derivative would still just be a constant term. Our yp double prime minus yp would be some other quadratic polynomial. If we chose the right coefficients of this quadratic polynomial, we might be able to get rid of the 3t and the negative 4 here. That doesn't happen with this particular solution, but let's now try a particular solution of the form at squared plus bt plus c. This makes a certain amount of sense. It doesn't have any powers of t greater than 3, so that it's going to be possible to, well, we're not going to be stuck with any powers of t greater than 3 when we evaluate this left-hand side. Now, the derivative of yp equal at squared plus bt plus c is just 2at plus b, and the derivative of that is just 2a. So that when we plug these derivatives back into our original equation, we get yp double prime minus yp equals 2a minus the yp, which is the quantity at squared plus bt plus c, and that has to equal t squared. If we collect our terms on the left, we end up with negative at squared plus bt plus 2a minus c equal t squared. Now, it's just equal to t squared, but let's just go ahead and and clearly write that we have 0t and 0 constant. If we're going to end up with t squared, we have no t, we have no constant. The reason I write it this way is because this left-hand side does have a multiple of t, and it does have a constant term. So this multiple of t is going to have to be 0, and this constant term is going to have to be 0. Also, our t squared term, well, the t squared term has to match up. We're going to get negative a equals 1. That's setting the coefficients of t squared have to be equal. And b has to equal 0. That means the coefficients of t have to be equal. And our constant terms have to be equal. So 2a minus c has to equal 0. This is 3 equations and 3 unknowns. And the solution to this system of 3 equations is quite simple. The value of a has to be negative 1. So let's just write down, this is 3 equations in a, b, c. Our conclusion is that a has to be negative 1 from this first equation, b has to be 0 from the second equation, and c, well, 2a minus c is 0, so c is going to equal the negative of 2a. I'm sorry, negative c is going to be the negative of 2a. c is going to be equal to 2a. So c is going to be equal to negative 2. Now that our Now that we have the values of a, b, and c, we can plug them back in here. Yp then is going to equal at squared, which is going to be negative t squared, negative 1t squared. Bt, that's going to be 0, and c is going to be negative 2. And this is going to lead to our general solution to the equation, where we add the particular solution to the characteristic solution. Characteristic solution, as we've known for a while, is c1 e to the t plus c2 e to the negative t, and our particular solution is negative t squared minus 2, which we just obtained.